Hi, this is Alex Yazdani. This is a demo for Lab 7 in EE533 in spring of 2025 with Professor Young Cho. My lab partners are Tim Liu and Szymon Gorski, so let's get started with the demo of the lab. So to start off, this is our pipeline code. We have the fetch stage, decode stage. There's some control logic here and a condition engine for those ARM instructions. There's an execution stage, a memory stage, and then a write back stage. We also have a Python assembler, which right now supports pretty much all data transfer instructions, and then just add, sub, compare, move, and then a couple branch instructions. So you just run this with the output of a GCC ARM code. So right here we have some, and we ran this with this file. It does two things. It first reorganizes it a bit, so it the branch addresses after this are absolute. It also unrolls certain instructions where necessary, and then after that it converts it to a binary, which we can then use as an input to our pipeline's test bench. So here I have a test bench. And pretty much it just loads IMEM and DMEM with pre-programmed files, and then enables the pipeline, waits for it to get to the end of the instructions, and then it just dumps everything. It dumps the IMEM, DMEM, the reg file, the CSPR flags, and then also the PC. So just to look at data.txt really quick, this is an unordered list, so it starts 9, 4, 5, 2, 0, 6, 3, 7, 1, and then 8. And so this program we have here is a bubble sort. And so if I run this really quick, so first compile, and then just run that. So down here we see the flags. The PC ended at 55, which was expected. These flags are as expected. This is the register file. There's nothing super interesting in here, but we basically can see the values of I and J, which are the two different incrementers in our loop. So we see that the execution finished through both loops, the inner and outer loop. And then up here we have a DMEM dump. So this is just the sorted list 0 through 9. These started out of order when we loaded the instructions, and now they're in order. Then up here, these are just the instructions. And so this was just simulated in iVerilog. So these are the memory modules, and the register file are behavioral models that we just created for the purpose of simulation. But on the actual FPGA, we've implemented them using IP cores. And we also did a simulation in Cadence SimVision. So I can hop over to that. And this is actually post-synthesis. We synthesized this pipeline design using the GSC 45 nanometer library. And the purpose of doing that was just since SimVision has a much more modern interface than Xilinx ISE, it's a lot easier to debug because we could see many more internal signals. And so this really helped to get the design working because, of course, pre and post synthesis simulations are very different. You need to actually synthesize to verify that it works. But so here, basically this first part, we're just loading IMEM, then loading DMEM, and then this, when pipe enable is set, that means that we're actually running the pipeline. Then we stop here, then this is just dumping IMEM, and this is dumping DMEM. And so then we just see the program counter here, so let's just zoom in somewhere. Oh, 19, 1A. Let's make this decimal to make it easier to read. So you can see here, it's going through the entire program. So here we see 36 and then some unsettled value and then 20. So this is actually a branch instruction. I'm not sure exactly what this was, but it's either like branch higher than or maybe just a branch. And have all these other internal signals that we can look at. Don't know if there's anything good. A lot of them get synthesized away. ALU result, for example. Let's just look at. So we can see that changing. This high value here is because there's a negative value, so that is as expected, even though it looks a little weird. And then over here, we see the same output that we saw in the pre-synthesis simulation. So here's the register file. And then right here, we see the sorted list. So yeah.
To briefly demonstrate our logic analyzer and how we are able to use our logic analyzers to debug our processor. So currently our processor has two built-in logic analyzers. The first one will record data from the EX mem stage register, and the second one will record data from IDEX stage register. Once our pipeline is enabled, the logic analyzer will record data for 255 consecutive cycles, and then it will stop. And after the pipeline finish its execution, then we can read out the content of our logic analyzer, and it will give us details of how instructions was executed cycle by cycle. So first, let's download the bit file. Let's do a reset. And then first, let's load the program into our instruction memory. And then let's load data to our data memory. And then we begin execution. And we stop it. And here we're going to examine the content of our logic analyzer. First, let's check the content in EXMEM stage. So as you can see, the first couple will be bubbles. And then right here you can see the PC value changes, and so it was recording value instructions. And then you can see here it is actually a memory accessing instruction. And let's do the same for our second analyzer. So this one records data from the IDEX stage register. So you can see here, yeah, basically you can see it has all the detailed information regarding each cycle. We are able to use this information to help us debug what's really going on with our processor. So yeah, thank you.